Good morning, everybody. What happened to everybody this morning? Only half of you here. Thursday. No, it's Thursday. No, some people are sick. I'm getting more and more emails about what did one student call it? The quademic. The quademic. Um, they were scoring themselves. I got 2 out of 4 on the quademic. Be careful out there. We've got, what is it? COVID, a RSV, a cold, and then norovirus. Yeah, so norovirus is stomach flu. So all kinds of fun things going on out there. All right, let's see. Did I start the roll this on that side last time? You guys don't remember? I'll start it over here anyway. Let's see where we can make it in the classroom today. I think that's the last time we're going to see the roll sheet. Thank goodness. Because as of Monday Census Day, you're locked in. You're mine. No, after this Friday, you guys can't drop without a W, I think is what it is. All right. I threw this one up on the screen, right? And some of you have had a chance to read it. We're going to jump straight in, but what I want you to do, since a picture is worth 1,000 words, and I haven't drawn a picture, what I want you to do is turn to your neighbors and draw this together, right? Try to visualize this one together. It can be a drawing of what's going on, lists, right, of things you know and you don't know. So I want to give you 5 minutes to really try to dig into this one and see what you can and can't visualize. And you might run into a little bit of trouble, but we'll see what happens. We'll see what happens here, right? Okay, so there should be a lot of talking, a lot of back and forth. Don't do this one solo. Help each other out. Go.
So it's really a setup to, yeah. That's how I've always been visualizing these problems.
Yeah.
Oh, look at, so with this guy too, if the car is a car, so this is both side acceleration brake is
At the end of this.
because right in the concept of this
For the car itself. Yeah. Well, the horizontal line. Yeah, it would be negative. Yeah, it would be negative.
Okay, so if we're drawing the degree, how do you know if it goes? Are you sure?
Because it says it's below the horizontal.
Well, yeah, no, yeah.
Okay, so if it was above, it would be.
It'd be opposite.
All right, how'd you do? Did you get this far? Yeah? Okay. Is that easier or harder with people?
Easier.
Some people with social anxiety, I'm sure, would answer the other direction, right? But like in terms of getting the physics out, it's often much faster. You fail faster with somebody else there, right? Get those mistakes out of the way, right? You are not expected to be perfect, well, until the exam, right? But like, just, you can't get this right off the bat. And you're probably learning that already. And so if you can get study buddy, study group, Discord, tutorial center, graph, something, right? Where you can talk these things out, right? The faster you talk them out, the faster you will figure out where you're going wrong, where you're going right. And your brain will learn how to do this stuff. Okay. How many of you like ran into problems, difficulties, like trying to get your lists or any of that kind of stuff? Yeah, where did it stick? Like, where did you run into trouble? Change in X, change in Y, especially like for this first part here. Okay. I taught you something last Tuesday, 2 days ago, about kind of what happens, maybe it was last week, about what happens if the acceleration changes. Do we have two different accelerations here? Okay, what's the first acceleration we have? 2.6, right? In this section, the acceleration is down the slope, isn't it? And then where does it change? Once it gets into free fall, because once it's in free fall, what's the acceleration there? Now we're into negative 9.8, right? And the acceleration for this section, negative 9.8. So what do you have to do when you have a changing acceleration?
Separate the components.
You've got to do different problems. You just have to do different problems. This problem is two problems, okay? There's a problem that exists on the hill. With that acceleration and that distance, that's not free fall. It's rolling down the hill. It's not in the air. None of that's going on, right? And then there's a problem where it is in free fall after it comes off the hill. If we can find the velocity of the car, the final velocity of the car as it gets to the end of the hill, what will that be for the free fall section? The initial velocity. And that's kind of what you do, right? You find final for one part, and that becomes the initial feeding in to the next part. So that's what we got to do, right? Our visualization is leading to a little bit of strategy. I don't want you to think that like visualize, strategize, do it, check it are these rigid, like you have to do those in order. quite often visualize and strategize are kind of happening at the same time. Every once in a while, we sneak in a little bit of do it, because sometimes you just kind of have to map something out to see if it's going to take you anywhere, right? This isn't a real, like, rigid step-by-step thing, but there is an order there. You want to make sure you're visualizing first before you're jumping in and trying to do math. So be a little bit loose with that. But so far, we have an idea that we've got to do a problem, right, that's different, okay, than another problem, and we'll feed them into each other. Okay, so let's tackle the hill. What are we going to do about the hill? What do we know about the hill? Like, do we have a list? Yeah, we got 2.6 meters, and it's positive. Why did I put positive there? Is it speeding up or slowing down? All right. The 75 meters. Okay, so what are we going to do here? Have we encountered a problem before that's been on a hill like this? A little bit. Do we need to break things up into components? We've been given an angle, haven't we? And, I mean, I suppose I could have an x component of that acceleration and a y component of that acceleration. I could have a delta y and a delta x, break that 70. That seems like a lot of vectors, doesn't it? Is there another way? A car accelerates with a constant acceleration along a straight line. What does that sound like? Where have you encountered something like that before? Chapter 2? Is this a chapter 2 problem in disguise? Notice that the acceleration and the change in x are all lined up with each other. The velocity will also be in that direction. What kind of problem is this? One-dimensional or two-dimensional? This is a one-dimensional problem. It looks two-dimensional because it's on a hill, but it's a one-dimensional problem. There is all of these vectors, the acceleration, the displacement, the velocity, they're all along a line. And so that means that we don't have to go in and find their vector components. They're already all in the same direction. So really, all we have to do is tilt our head. Oh, straight line. You're like, Mr. Balogh, that's a trick. Okay, it is, sort of. But it isn't. We're taking advantage of the physical properties of the directions of these things. All of those directions are lined up, okay? In projectile motion, once this car leaves the cliff, we do have to break it up because its motion, its delta x and its delta y, are different from its acceleration. Its velocity vectors are constantly changing. So there we do have to break that up. But as long as we're on the hill, we're really just doing a one-dimensional movement along a line. All my vectors are added up. So this really is a chapter 2 problem. And now you know, and knowing is how you know stuff. Okay, 75 meters. And then, do we know how long the car was rolling down the hill? Do we know how long it took for it to roll down? No. Do we know how fast it was going initially? It was at rest, wasn't it? Do we know how fast it's going at the end? No. Is there anything else in the toolbox I could write down from chapter 2? Not really. So, I want my final velocity. I don't know time. So what equation are we going to pick? Do I need to write them back up on the abomination? It helps? All right. Black again. All right, from chapter 4, the chapter 4 versions, Can you guys see those? And what was it? Vy squared equals v naught y squared plus 2ay delta y, and then a delta x equals v naught x times t. All right. So there's the chapter 4 version. What do we need to do to make it a chapter 2 version? Ignore the bottom one, right? And make everything up there an x if it's horizontal, or a y if it's vertical, right? In this case, we're going to call x down the slope, right? Okay. So we need an equation that doesn't have time in it. Third one. Right? So if we use the third one, we can find the final velocity. Really, all we have to do is take a square root, don't we? So my strategy, use the third kinematic equation. I'm not even going to put x's on it or y's on it. It's all in one dimension, right? Okay. And solve it for the final velocity. 0 squared plus 2 times a 2.6 times 75. And bim bada boom. I got 19.8, 19.75 meters per second. Positive or negative? It is a square root right there. Positive. We said positive is kind of down the slope, right? So we know it's moving. Okay, so now that we've done the first part, of which the problem hasn't asked us anything about, but is very necessary for us to figure out the rest of it, right? Now that we've done the first part, what do we know? We know that the car leaves the cliff moving at 19.75 meters per second at an angle of what? 15 degrees below the horizontal, right? And the instant, now that we're in projectile motion, and now that we have an angle and an initial speed, and the thing that half of you forgot yesterday for a good half an hour, you come up to me, Mr. Balogh, it's not working, and I'd say, yep, you're right, it's not working, you made a mistake. Well, can you help me? No. Remember that yesterday in lab? What was one of the things you forgot? Split the component, right? Get the components of the velocity. So let's do that right away. Before I even visualize anymore, I've got a velocity. I'm going to break this up, right? So V naught x. My x component, right, of this velocity. I'm going to have x and y components, right? The x component right here, is it touching my 15 degrees? Sure is. So cosine, right? So it's going to be 19.75 cosine 15 degrees. And some of you are in panic mode right now because I didn't write negative 15. Don't worry. Okay, so I just got magnitudes here, right? But what direction is the velocity pointed, like positive or negative, for x? Positive. What direction is it pointed for y? This is where I'm going to put my negative sign. And why do I have to put that negative sign on there? It's going down, right? It leaves the cliff going horizontal and down. What's that? Sure, inward. Yes, thank you very much. Okay, so I can go calculate what these numbers are, maybe. I hope I did this right. I got 19.1. That's a positive 19.1 and a negative 5.11. Again, I'm doing a little check right here, right? As I get a number, I have to ask that number, why are you positive? And if I can't come up with a reason, I got to go figure out a reason. Why are you negative, right? Like maybe I just write down 5.11. You stop, you say, is it positive or negative? And how do I know? Well, it's going down, so I better put a negative sign on it. The math doesn't do the talking, the physics does. All right. What am I doing? Okay, so I got those two. What do I do next? Well, that's where we want to go, but my visualization isn't done for the red portion yet, is it? So what if you're lost, if you're not sure what to do next, you flip back through your notes and you see that we made a list. When you're lost, just start making a list, right? Start going through and seeing what numbers the problem's giving you. What numbers are implied, right? Are there words like dropped or at rest or stopped, or, right? Like you're looking for data, for information, right? And as far as the list of things we can know and not know, I go look at my tools, right? And so final velocity, acceleration in the y direction, time, delta y, delta x. I think that's the rest of the things because we already got v naught x and v naught y, right? So for the red portion only, do we know how fast the car is going vertically when it strikes the ground or water or whatever? No. And we know that that's not going to be 0. Because if you put 0 into a projectile motion problem, right, where something's in free fall, what have you just told it? Max height. Is this thing at max height? I mean, no, it's just no. Okay. Do we know the acceleration in the y direction? No, it's not g. Negative little g, or negative 9.8 meters per second squared. Why negative? Going down. Do we know how long it's in the air? No. Do we know its vertical displacement? Yes. It told me it was a 150 meter tall cliff, but what am I going to put in? That was the second mistake a lot of people were making yesterday, right? Some of you were coming up, it's been no working. And I'd be like, yeah, you made 2 mistakes. And you'd be like, well, thank you for that. That doesn't help. I was like, I know. But you fought through it. You got there. All right. 150 meters, negative 150 meters. Again, the minus sign. How many of you are prone to forgetting to check for those minus signs? Okay. What are you going to put on your cheat sheet? At the very top and like in highlighter or something. Check your signs. Right? Because you're going to get into the exam, right? And you're going to be in this room and it's going to be all like stressful because Mr. Bale's going to be walking around watching you. Right? And there's going to be a lot of silence. And the silent, there's like a high frequency sound that the brain makes when it's being tortured with physics, and you'll all pick up on it, but we just won't hear it with our ears. And I'll make sure to turn the amnesia generators on high in the walls. We had those installed especially. It's wonderful, right? You turn them on for exams because you walk through the door and what happens? You forget everything, right? That's our fault. I'm joking, of course, but not really. So you'll have all of that, and then you'll sit down, you'll pull out your cheat sheet, your summary sheet, and right there at the top, it'll say something like, check your signs. Or hopefully something like, you got this, you can do this, you've done it before. You can fill up the rest of it with equations or whatever, right? But leave some notes to yourself, right? Things that, you've taken tests before, you know what you forget. You know what your blind sides are, right? Get those down on the page, right? Notes to yourself. Very powerful. Okay, do we know how far horizontally it went? Nope. Oh, now I'm going to check and see what they actually are asking me for. How far from the cliff horizontally? So part A is asking for delta x, right? Can we get delta x if we don't know the time? No, so okay, fine. Can't do part A. How long is the car in free fall? What are they asking for? Part B, how long? What are they asking for? Time, right? So part B is the time right there, right? What is the magnitude of the velocity of the car when it strikes? Okay, so basically they're asking for everything, right? They want us to find a delta x, which means we need to find the time. But they're also asking for the time. But in addition to the time, they're also asking for the final velocity. So what's our strategy? What's our plan? Okay, so you're going straight for third equation. Is that because you don't like quadratics? Or okay, all right, that's fine, right? Okay, avoid the quadratic at all costs, right? Couldn't the second equation, can it just give us the time? Sure, right? And if we're confident in our quadratics, great. We can then use that time to find delta x and Vy, right? Of course, I would do it both ways. Third, first, second, see if I get the same times, right? All that kind of stuff, right? As a check. On an exam, time is kind of tight, right? So pick one, do the problem, do the rest of the exam, and if you have time at the end, then you can run back and do a check, right? So again, different brains, different mathematical abilities. I think this time I'm going to use the third one and then the first one and see where that gets me. So what is my plan here? Use the third kinematic equation. I'm just going to say it out loud. 2ay delta y. That's going to get me Vy, which is part of the answer for C. Why is Vy not the magnitude of the velocity? It's only one part, right? It's only one component of it. So we need both the x and y components, and we need to put those together. Okay, so this will get me the component, and then eventually I can put that into this one to find the time. So let's see here. Vy square root of negative 5.11 squared plus 2 times a negative 9. I'm getting nervous. A lot of negative signs under this square root. Oh, there we go. No imaginary numbers today. I got 54.5 meters per second. That's a plus or minus, isn't it? So which one do we pick for when it lands down here? Or right before it lands? Why the negative one? It's going down. Okay, and so that's what goes up into here to solve for my time, which is going to be Vy minus V. I'm doing algebra really fast now. So negative 54.5, because this is not a math class, minus a minus 5.11 all over a negative 9.8 got me 5.04 seconds. So there's my time. I could go plug this into my quadratic solver, which I did, and I got 5.036. So, you know, that's the same thing, right? So pretty good check right there. And then, so I got the time. That's the answer to B. How do I find how far from the cliff? Then I'm going to use delta x equals V naught x times t. V naught x 19.1 and the time 5.04. No real checks here other than can you use a calculator? 96.1 meters. So there's the answer to A. I've got the answer to B. And to get the answer to part C, with this 54, that's not the answer right there. It's a piece of it, right? When it strikes the water, it's going down at 54.5 and it's going sideways how fast?
2.6.
No. 19.1. Why is that the same as it was the initial x? No acceleration in the x direction, right? What we start with, we end with in the x direction. Okay, we're looking for that right there. So what do? Square root of what? 4.5 squared. And I get a total of 57.7 meters per second. They asked for magnitude, right? It's just the number. If they asked for direction, I could do an inverse tangent there, right? To find out what that angle would be. Hey, 30 minutes. A lot better than the hour we spent last time, right? Are we getting better at this? No, Mr. Bale, I haven't tried my homework at all. I have no idea what's going on. You will. You put in the hard work, you're going to get there. Let's do a quiz and see where we are at in our conceptual understanding. All right, I want to, before I do this example, I want to do something else. And we'll get back to finding initial velocities in a minute. But I've got a setup here, and I've got to start setting it up while I talk. So this is a little bit like juggling, right? Okay, I got to do two things at once. But I'm going to set this up. We're going to do an experiment live, which means it's probably going to fail at some point, right? But we'll see where we can get. And I need to move my computer. But unfortunately, this experiment was made in a day and an age where we're not allowed to talk about things anymore. Specifically, let's see. I've got to sanitize this exam. I've got to update it to make it more acceptable for the modern crowd. So let's see. A wildlife biologist is tasked with studying monkey. Oh, I can't say monkey. I can't say monkey because the apes get mad. Primates. Is tasked with studying primates. Okay? And to study these primates, this wildlife biologist has to can't say the word shoot. No. It's too charged a word. Okay, neutralize is even worse. No, we just need bigger words so people don't understand. Anesthetize. Has to anesthetize the primate so as to be able to, you know what, to heck with it. A hunter is hunting monkeys. And they've got a big gun. They got a blowgun. Okay? And, so monkey is in a tree. How do you know it's a monkey? It has a tail. Curious George took my daughter to point this out to me. He's a good little monkey. What does Curious George not have? A tail. The man in the yellow hat's got some explaining to do. That's all I'm saying. All right. So the hunter has a blowgun and aims the blowgun directly at the monkey. Okay? Like sights down their blowgun and points it directly at the monkey. And they're going to shoot a dart. The monkey said, aha, God, stupid hunter. I'm going to, as soon as the hunter shoots, as soon as the dart leaves the end of the gun, I'm just going to let go, right? It's aiming directly at me. I'm going to drop, right? And the dart's going to go sailing over my head. Turn to your neighbor. This isn't a quiz. Turn to your neighbor and discuss. Does the monkey get it or not with this setup? Go. All right. How many of you say the monkey gets it? Monkey haters. Why are you saying the monkey gets it?
Because the dart falls with the monkey.
Okay, I've got the setup right here, right? And what I've got here in the front of the launcher is a laser, okay? And the laser sits in the barrel, okay? and gives me like the exact aiming point. Jesse, can you verify that it is pointed at the monkey? It's a bit high. I'm not going to adjust it, okay? This is the monkey. Happy monkey, sad monkey, what do we got? This is a pretty happy monkey, right? This one's hanging by its tail, but you get the idea. Okay, right? Get on there. All right, okay? So what I've got is an electromagnet right here, okay? And the wire, okay, goes down here, and there's a little switch on the side. It's kind of hard to see. But as soon as the ball leaves the end of the gun, it's going to hit the switch, and it's going to drop the monkey, right? Okay, it's going to cut the power to the electromagnet, and the monkey's going to fall. So we've got the same setup as we have, right, in the conceptual thing, okay? Roughly aligned. We'll see. We might have to do this more than once. It'd be great if it did it the first time, right? This is real world physics here. So here's my projectile, right? I'm going to put it into the gun. And those of you that say that the monkey gets hit, what's your justification? Gravity. Okay. All right, so you're saying that as soon as the ball leaves, it's accelerating down. And the monkey's also accelerating down. But yeah, at the same rate, I agree, right? They're both in free fall. But the monkey's up here. The ball, yeah. Isn't the ball going to do like a... Let me just give it away right now. It's independent of the speed at which I launch that. Speed doesn't matter. This could be a high-power rifle or the slowest dart in the world. If it's too slow, the ground gets in the way. But other than that, right? But what's the justification for the monkey getting hit? All I've heard is gravity, which isn't a justification at all. So?
So it's lined up with that.
Physics. So what you are saying is that if the monkey gets hit and they're both in free fall, then this ball has to fall the same distance as this monkey in the same amount of time? Trishan? What's that? No, I could put this closer as long as I'm aiming at it. That's the condition. If I'm too high or too low, it's going to be a little bit off.
It's just like Rio wants the balls, but instead of it shooting that way and dropping.
So instead of perfectly horizontal, now wait a second. If a ball is launched upwards at the same time another is dropped from the same height, which one's going to hit the ground first? The one that's dropped. Why? Because the one shot upwards takes more time in the air, right? Well, isn't this ball going to take more time to come up and come down than this monkey is going to take to fall? They're not at the same height, and they both don't have the same initial speed, right? So so that example cannot be conflated with this one. There are differences here, very important differences. Should we just see what happens? Okay. It happens fast, so I'm probably going to have to repeat this several times, especially since I'm probably going to miss anyway, right? So, if you want. Oh, I put the ball in there. So we're roughly lined up. Okay, please work, please work, please work, please work. Okay, I'm going to take the thing out. All right, we ready? Happens fast. 3, 2, 1. Yes! Took me 45 minutes to set that up this morning. I'm so mad. Okay, thank you. Right? Did you see it? It hit the monkey on the way down. The monkey deflected and the ball didn't keep. I forgot to warn you guys. Right? And it hit, right? Okay? Hit it right. So now the question now is why? Those of you that wanted the monkey to be safe, I'm sorry. The monkey did not argue correctly. What should the monkey have done? Not let go. Right? Okay? The monkey should not have let go. So let me see. Can I get this to work? You did? Okay. It better be on TikTok, Facebook, and all the social media. And I want part of the revenue. All right. So here is a video of the same thing. This is my backup.
This brass tube points directly at a plastic bottle hanging from an electromagnet. If we put a wooden dowel in the tube and blow into the tube, the dowel is fired straight at the hanging bottle.
They made this
But
PC.
as the dowel flies out of the tube, it knocks off a piece of aluminum foil carrying current to the electromagnet. The electromagnet shuts off, and the bottle begins to fall just as the dowel flies out of the tube. Even though the
Right.
bottle is no longer in the spot at which the dowel was aimed, the dowel still strikes the bottle. Here is a repeat with the dowel fired at a lower speed.
You see how it still hits?
These dots will track the positions of the dowel and the bottle at 1/10 of a second intervals as the last sequence is repeated.
So really, other than the ground just getting in the way, right? Assuming there was no ground, eventually, no matter what speed this thing's shot at, it's going to hit, right? Because it's true. Both of these objects fall the same distance in the same amount of time. The monkey does it just purely vertically, right? And let's say it goes 75 centimeters, okay? What is this ball going to do in the same amount of time because it has the same acceleration? It's going to fall 75 centimeters. But that 75 centimeters is going to be on the way up and on the way down. As long as this thing is pointed directly at the monkey, it will hit every time, assuming you get things lined up correctly.
Is that because technically it's like at the same angle? So if you
It's
if you
not so much the same angle. You just have to be pointed directly at,
so
right?
kind of if you're anyway like this.
So if the monkey and the thing were at the same horizontal, and this sometimes is easier to picture, right? If it was perfectly horizontal and the monkey lets go at the same time the thing is shot, everybody agrees. Well, they fall at the same distance in the same amount of time, right?
It was easier to look at that because it
Yeah.
had it connected to each other.
Yep. Yeah. All right. Oh, success. You guys are so worth it. All right. So that was that. Okay. I'm going to start something. I may not finish it. This is big. This is big. What we're going to do, I don't do this very often in this class, but I just need to kind of show you the behind the scenes a little bit of what it means to be a physicist. I do try to teach this class like you're all engineers and application, right? I teach you toolboxes. I don't show you where the toolboxes come from, all that kind of stuff. What I would like to do is be a little bit of a physicist right now, if I may. You have no choice in the matter. And I want to derive something for you. Normally, if this were, most physics teachers would spend all their time deriving everything and not showing you how to use it. I kind of flipped that script a little bit. But what I want to do is not only derive something for you, but give you a reason for why physicists do this. You see, physicists, we don't like math. Some do. They're weird. We call them theorists. Most physicists want to solve a problem once so that we never have to do it again. If we can solve all of the problems once, we'll do it. And so that's what I want to do. I want to solve every problem that involves not knowing the initial velocity. So up to this point, right, all of our examples, we've been told how fast it's going when it launches, okay? This time, we're not going to know how fast it's going when it launches. So how would we approach a problem where that might be the case? Warning, there is a lot of math ahead. But let me set up a situation, okay? There are some things that we will have to know. For example, we're going to have to know what angle this thing is shot at, okay? It's not impossible if you don't know that, but it's much harder if you don't, okay? We don't know the initial velocity, but we do know the angle. So let's make a list of what we're going to know. We're going to know the angle. We're going to know delta x. and we're going to know delta y. So this thing's going to do something, okay? It doesn't have to be at max height. This is completely arbitrary for any delta x and any delta y. But we're going to start with knowing only the angle, the delta x, and the delta y. Those are just given things, right? So I'm not left with much, right? Okay? There isn't, I mean, so what? I have an angle, right? Oh, and we know the acceleration in the y direction, don't we? Sorry, I guess that one's implied, right? Okay, it's negative g. All right. So the way that you approach this, knowing that you have delta x and delta y, is you use the only two equations you've got, really, with delta x and delta y. Now the third one I know has delta y in it, but we also don't know anything about the final speed, okay? So we want to avoid final speed. So really, it's the second equation and the fourth equation from the projectile motion toolbox that we are going to use. And what I just taught you is the overarching approach. When you don't know the initial velocity, you just default to using the second and fourth equations. But we're going to go one better in that we are going to try to solve every problem all at once. And we're going to do that with a derivation, and it's going to be all symbolic, which I know you guys absolutely love. You just love those symbols, right? No, you don't. You always like your numbers. Okay. Is there anything that's the same between these equations? V naught y and V naught x are not the same thing. I heard it. Starts with a T, ends with an I'm. Okay, time. Time is the same. So that kind of suggests something, doesn't it? But before I even get there, there's a bigger problem. It happens to be a mathematical one. How many unknowns do I have? Well, let's count them up. So V naught y is an unknown, right? 1. T, unknown. That's number 2. Okay, we haven't had any repetitions. Delta x, V naught x, third unknown. T we already took care of, right? We do know the angle, but we've got 3 unknowns in my 2 mathematical statements up there. Any math majors out there? How many equations do you need if you have 3 unknowns? Minimum 3 equations. And there's other considerations, but we won't get into that, okay? So I've got 2. I need a third one. Michael, what did you just say? We know the angle. And this is how we're going to link it all together. Because V naught y is equal to what? Sine theta, because this component is not touching the angle, isn't it? All right, and V naught x? All right. So let's get them in there. Delta y equals V naught sine theta t plus 1/2 ay t squared. And over here, I'm going to have delta x equals V naught cosine theta t. All right. Now we are down to 2 unknowns, aren't we? V naught and t. I've got 2 equations, 2 unknowns. Mathematically, this is possible. For me, maybe not. I do have notes, so I'm pretty confident I can get there. Got to get rid of t. We want V naught, right? So let's get rid of t. They're not asking for t. We want to find the initial velocity. Don't care what t is. I'm going to solve this one for t. That's going to be delta x over V naught cosine theta. And then this t is going to get inserted into here. And this is going to blow up. And it's going to look nasty. So just hold on. Just hold on. All right. I will not ask you to derive on the exam. I just won't, okay? I'm more concerned, do you know how to use these, right? Can you show me correct physics and its application? But what we're about to get is very useful in a lot of different ways. Okay, so I shove that in there, and oh my gosh, my life becomes terrible. Sine theta, and now t, right? This is a delta x over a v naught cosine theta plus 1/2 ay, and then delta x over v naught cosine theta, squared. Oh my gosh. Don't give up hope. Okay, first term. Oh, magic. What happens in the first term? I'm happy, not only because something canceled, I'd be a little bit worried if it was the thing I was looking for just completely canceled out. But more importantly, I was staring down the barrel of a quadratic equation. I had a v naught and I had a v naught squared, which was worrying me a lot. But now that one of them has gone away, at worst, I'm going to have a square root, right? Okay, that's good. What's sine over cosine? Oh, other math classes coming in. So this is delta x tangent of theta, isn't it? What's left there. I have no clever things to save you for over here. It just is bad. Ay all over 2 v naught squared cosine squared theta. I got it. The 2's down in the bottom and the ay's on the top. Okay. But yes, thank you. Always check me because I tend to lose factors of 2 all the time. Let's move the delta x tangent theta over. Again, I'm after v naught squared, so I kind of want to get it all by itself. 2 v naught cosine squared theta. And then I'm going to do a flip-flop here. I'm going to take this side and move it up to the numerator there. I'm going to take this numerator. I'm going to move it down to the denominator. Multiply both sides by the denominator and divide both sides by the numerator. It's the same thing. It's just my brain thinks of it differently. So this is 2 v naught squared cosine squared theta equals delta x squared ay all over all this junk, delta y minus delta x tangent of theta. And now I can take this 2 and this cosine squared theta and get them down here. Delta x squared ay, running out of room, 2 cosine squared theta, quantity delta y minus delta x, tangent of theta. And now I've got a v naught squared on this side. So what am I going to do to both sides? I am going to square root it. So here we go. Delta x squared times ay all over 2 cosine squared theta delta y minus delta x tangent of theta. What is in the box? Not the answer. All the answers. For every problem where you know the angle, and you know delta x, and you know delta y, you can find the initial speed by using that. I don't think it's in the book, okay? It's one that I would put on my cheat sheet, or I'm not going to put it in the toolbox per se. It came from the toolbox, but it certainly would save me time, right? Say on my homework, okay? If I had this equation in my back pocket, okay? If you take a careful look at the topics list on the exam that I posted this morning, you'll see that one of them says find initial velocity. Could this be useful? Okay. So let's talk about that. Michael?
Did we not care about the negative?
What negative? What did I miss?
When you square root the square, you get a plus or minus.
Oh, plus or minus? Okay, yeah. So I was kind of going to get there, right? What do you put in for AY? negative 9.8, meaning that the acceleration is pointed which way? Down. Okay. So for the picture I drew up there, what do you put in for delta x and delta y in terms of like their signs? They would both be positive, right? But what if instead your delta y were negative? What if this thing went up and came down and was below where it started? What would you put in for delta y? A negative. So all the same rules apply, right? For checking your signs and making sure you're putting in the right thing. Delta x is almost always positive, right? Stuff doesn't go to the left. And then if we end up like instead of delta y being measured up there, it was measured down here somewhere, we would have to have a negative delta y. I saw a hand back there somewhere. Gerson. The three unknowns we ended up with were time, v naught x, and v naught y, right? But we got rid of the v naught x and v naught y by taking advantage of their vector component definitions, v naught cosine and v naught sine. So we really just need to know theta, delta x, and delta y. The acceleration y direction's a gimme. So yes, we just figured it out for the moon too, right? Pick favorite planetary body, put the correct acceleration for gravity, and you're done. Okay. But this is kind of what physicists do, really. We try not to solve one problem at a time. We try to solve a problem for every bit of input we could put in there, right? We avoid math by doing less math. This is less than if I had 5 of these problems and I put numbers in and had to redo this process every single time. You might disagree. Maybe you like the numbers more. But that's really just arithmetic. I'd rather not have my TI calculator lie to me and have problems with parentheses, right? I'd rather just have it done once, right? Which is why you'll see me constantly do stuff in symbols, right? Symbolic notation and doing it in symbols allows me to solve every problem, right? For any input, right? I can go back and do the car rolling off the cliff problem for any acceleration off that cliff, for any angle, right? By doing it symbolically first, right? You just have to learn how to be careful about where you can apply this. Now, I think in your homework, one of your unknown initial velocity problems, I think, tells you like it's at max height or something like that, okay? The problem becomes a little bit easier when you know something has achieved max height, because what do you know about the velocity up there? It's 0. And so you can actually quickly sometimes just get the time and then plug that time into another equation and get the initial velocity, right? So I'm not saying this is to be all that. I am saying that this will work even for a max height problem, right? This doesn't care if it's at max height or not, right? So yeah, we do a lot more math to save doing any math later, because I can do this and then have time for lunch. If I'm brute forcing a bunch of problems, I'm going to run out of time for lunch. And physicists always want lunch. And breakfast and donuts and whatever else. I don't like donuts. Don't bring me donuts. All right. I'm going to stop there. We're about 5 minutes early, but that's okay. I have filled your brain quite enough. Next week, let's talk about next week. What are we going to do on Tuesday? I'm going to finish up a little bit more of chapter 4. I'm just going to do more examples, right, of things. We'll talk a little bit about the exam, right, and what to do. Wednesday's lab is review, okay? So for 2 hours and 50 minutes, you're going to come in. I'm going to use about, 45 minutes of that to answer your questions, to talk about the format of the exam, to get all the heebie-jeebies out, right? All that kind of stuff. The rest of that time is going to be like grasp for you to finish up chapter 4 homework and all that kind of stuff, right? So that it's for you. It's not for me. You have to come with questions on that Wednesday. And then Thursday we'll take the exam. I will see you next Tuesday. And please bring me the roll sheet.